Welcome everyone again. Let's now have the final activity of the day, which, as you probably remember, is going to be a panel discussion among 4 lead researchers in the field. And in particular, we have here today with us Janet Anders, Nicole Harpen, Mauro Paternoster, and John Gould. So what we are going to do is that the 4 of them are going to share their perspectives on open questions and ideas in the field. So what we would like you to do to start with is if perhaps each of you can introduce yourself to the audience. I'm sure that many of you know you already, but just to make everyone at home. And then you can start the discussion as we previously discussed.
Okay, maybe I go ahead and you mentioned me first. So yeah, thank you very much, Jesus. And firstly, thank you 3 actually for organizing this event, which is really fantastic. I'm very pleased that it's such a nice event. So many people have come, and the program is really fantastic. So well done for organizing it. Really great initiative. I would also like to point out briefly that it's quite an Exeter heavy thing, isn't it? Because one of you has been an undergraduate student at Exeter, one of you has been a PhD student at Exeter, and one of you is a postdoc at Exeter. So yeah, well done. Yeah. Great. So okay. So yeah, I'm Janet. I lead the group at Exeter, and so that's the connection. Well, quantum thermodynamics is a little bit sort of a baby that I've been looking after for a while, together with others, of course. But it's a really interesting field that you all obviously are interested in. I found it a little bit, let's say, Jesus, what did you put on the webpage? We're going to answer all questions. The panel will answer your questions. Just go ahead, ask. I'm looking forward to having many questions that I will not be able to answer, because quantum thermodynamics still is a very young field. There are many unanswered questions. We are still, in some parts, we're still trying to find the right questions. Because it's such a young field, sometimes it's not even clear how to put the question in the right way yet. So that's really the sort of introduction, and I give over to Nicole to say a few words.
Thanks very much, Janet. I'd like to echo your thanks to the organizers for putting everything together, and also for the opportunity to talk with people here. So I'm Nicole Younger-Halpern. I'm currently an ITAMP postdoctoral fellow at Harvard, although shortly I'm going to be moving to Maryland, to the National Institute for Standards and Technology, which shares some quantum institutes with the University of Maryland. I'm building a group there, and we'd like to make Maryland quantum thermodynamics central for North America. So if you're ever in the Washington, D.C. area, then please do stop by and talk quantum thermodynamics with us. I have been so delighted in my fewer years than Janet's in quantum thermodynamics to see the foundational insights that have been provided. We've learned a great deal about how quantum systems can perform thermodynamic tasks in ways impossible for classical systems, and that has shed light on the difference between classical and quantum physics. We've also learned more detailed versions of things like the second law of thermodynamics. Now, I would love to see, in addition to more of that work, because as Janet said, a lot needs to be done still, I would love to see progress on really practical technologies. So people have definitely proposed technologies within quantum thermodynamics, for instance, engines and batteries and so on and so forth. They are great in shedding this foundational light and helping us understand how quantum differs from classical, and how we can improve upon some figures of merit in the quantum regime in ways that we can't in the classical world, but still, even to cool a system down so that it can exhibit quantum behaviors takes loads and loads of energy. So it would be, I think, wonderful to draw upon the spirits of the Industrial Revolution, which gave birth to thermodynamics, and also gave birth to very, very practical machines that were very worth investing in. I think it would be wonderful to find opportunities for some of the foundational insights that have been had in quantum thermodynamics to have really practical, useful, even from a company's perspective, implications. I'll pass along the torch to the next person.
Go ahead,
Yes.
Mauro.
You sure, John? Yeah. Okay. Hi everyone. Mauro Paternostro from Queen's University in Belfast. I'm part of the quantum technology group here, and I'm also the head of the School of Mathematics and Physics, and this is the reason why I don't have a life anymore. But when I managed to forget my hat as a head of school, say, what am I interested in say, thermodynamics wise? So first of all, I'm one of the agnostics, so I think there is no quantum thermodynamics, or there is just thermodynamics, and what we are doing is developing a framework for the use of what we have learned on thermodynamics over these years and decades to the quantum domain. So it's always with a little bit of skepticism that I address this area. In terms of topics, so I'm getting old, so I'm more and more interested in simple things, and but I think that the two. So I think Jesus and Harry and Charlie, they asked for a couple of points each. And I thought about the two, and I think I have the 2 points that are interesting me at this stage. So one is trying to see really how we can draw some form of energetic blueprint for quantum information processing, and whether the lessons that we are learning from this framework, from the development of this framework for thermodynamics of quantum open system dynamics or quantum non-equilibrium processes, if that is useful to understanding, say, how to the understanding of how much is costly at the energetic level to implement information processing, say, whether this is say computation or a piece of simulation. At the end of the day, you want to compete with current, say, silicon-based technology, and one way to claim for an advantage might be that of an energetic advantage stemming directly from an explicit quantum operating regime. And in order to do that, we need to have a clear idea of how to quantify, characterize the performance of gates. Just saying it in very simple terms, and that spurs or gives rise to a series of questions linked to okay, how do you characterize the loss of performance of these transformations. So that is something really interesting as far as I'm concerned, and that is missing somehow from the panorama of problems, the breadth of problems that people interested in quantum technologies have listed. For instance, I mean, to my disappointment, is nowhere in the manifesto for quantum technologies that the flagship has brought forward, despite, I think, quite a lot of pushes coming from the likes of Janet, myself. I can speak for myself, my group, and I'm sure that other colleagues working and active in the area have done the same. So I think this is something missing, something needed, something that I'm certainly having fun, say, exploring, and that maybe say this whole sector of quantum technology is interested in really practical implementations would have to face sooner or later. The second point is more for fun, and is linked to the control that we have been applying to this open system and non-equilibrium open system processes. I think Owen today from the group of Steve Campbell spoke about say certain aspects of control. There are other ways to control the thermodynamics of these systems, and because I'm interested in machine learning as well, I'm really pushing and I'm trying to lure as many students as possible into that. I'm really interested in the combination of techniques for control based on machine learning based optimization and the performance of non-equilibrium processes, the operating performances of non-equilibrium devices. So we have a series of say papers, seeding papers that illustrate that indeed the combination is possible, still scratching the surface of, in my opinion, of a very big piece of rock that will need to be ditched at some point, hopefully soon. So these are the two questions that I think are partially addressed, hopefully will be more extensively addressed in future, but that I'm mostly interested in. Okay, John, the stage is yours.
Thanks, Mauro, and thanks to the organizers for inviting me. Unfortunately, I didn't get to see many of the talks, but some of the guys in my group were attending and had a lot of good things to say. Yeah, so I work in Trinity College Dublin, and I'm a group leader in a group that's interested in the sort of interface of non-equilibrium, many-body dynamics, and I would say energetics or thermodynamics. I guess like Mauro and Janet, and perhaps unlike Nicole, I mean, I did my PhD at a time where it wasn't in the topic of quantum thermodynamics at all. I actually come originally from a background in cold atoms, and my interest was always sort of rooted in many-body physics and statistical mechanics. And I guess I got interested. It's interesting that I got interested in sort of thermodynamics only as a postdoc, actually, around that time and it's still a thing in cold atoms experiments. I mean, it's kind of unique in the sense of many-body physics because it's the one area where, unlike condensed matter physics, you can observe unitary coherent dynamics of a large system over timescales that would typically not be reachable in condensed matter physics. I started to get interested in fluctuations and how you could use things like work statistics to describe quenches. And that's kind of brought me into the area. And then I kept sort of studying and trying to sort of find sort of linkages between the sort of stuff that was being developed in quantum thermodynamics and the stuff that was going on in many-body physics. More recently, I would say in the last couple of years, I've become more interested in what I see as being one of the sort of frontier topics for the quantum thermodynamics sort of tools to be applied to, which is sort of non-equilibrium steady states, which are the ones that you generate typically by, connecting multiple bats to a many-body system. I feel that that's still relatively poorly understood in the modern language, and so I'm investing a decent amount of time at the moment to sort of develop methodology with my group to describe those type of scenarios, which are becoming increasingly relevant for experiments. So yeah, I mean, I guess my interest has been rooted in sort of what's going on in the domain of strongly correlated many-body systems, and I find myself increasingly more interested in numerical descriptions, actually, because when you deal with complex systems, I mean, often your ability to do sort of exact calculations becomes compromised, and so we also invest a lot of time in that. So as for a field in itself, I mean, I'm always I wouldn't say skeptical is maybe the wrong word, like Mauro said, but definitely a little bit cautious that, whatever we do, that we're sort of rooted in physical realizations and what can be done in laboratories around the world and what's interesting for experimentalists, etc. I think is really important. I mean, I enjoy formalism a lot, and I know there's a lot of that going on in the community. But again, I mean, I'm always a little bit wary of directing sort of students down that path of just studying formalism for formalism's sake. I mean, it's always good, I think, to have physical platforms in mind, because at the end of the day, you have to be able to describe experiment. I mean, that's part of your job as a physicist. So yeah, so that's sort of my interest: non-equilibrium steady states, intersection of many-body physics and thermodynamics, and this type of thing.
Okay, thank you, everyone. It looks like we are having some questions already, so this is great. So something I will say before we go to the particular questions is that you all four have mentioned very, very interesting topics and very interesting threads. So I suggest that we can drive discussion both with the questions and some of the places you have touched, for example, technological applications, what it implies for foundations, etc. But let's start with one of the questions by Soumitra, who is asking to you, what do you think are the most fundamental open questions in quantum thermodynamics today? So I presume that you have touched a bit on this, but perhaps you can give a bit more concrete outlook of this question. Mm-hmm.
Yeah, whichever, yeah, Mauro.
Oh, yeah, whichever you prefer, yeah. Mm-hmm.
Am I jumping the queue, or is that okay?
No, there is.
You talk about the fundamental questions, Mauro, because I wanted to talk about some other questions.
Okay,
Yeah.
Okay, that's fine. Yeah, to me is, or at least my own fundamental question, or the question that I think is really key, at least for the understanding of the part of work that I'm doing, is finding a thermodynamically consistent formulation of open system dynamics in regime that go beyond weak coupling and, say, tameable and tackable limits. So the moment you start working in regimes where, say, you have interacting particles that are interacting with coupling strengths that are not necessarily weak or semi-weak, and you have multiple temperatures. Okay, so I'm seeing someone sharing a screen. I hope. Yeah. Can I go on? Yeah.
Yeah, it's me.
Okay,
I'm trying to share my screen.
Sorry.
Yeah, please go on. But yeah. I don't think it's showing, is it?
Okay.
It is. Your screen is showing, Janet.
We are seeing your
really?
screen, Janet.
I can't see it.
Yes.
What are you seeing?
I can see your screen. Otherwise, I would not have bothered you, Janet.
Keep going. Sorry.
No problem.
So, no. I wanted to support what you're saying with what I'm sharing, but I'm not sure I'm doing the right sharing. So
it's okay.
Is that the English football team supporters club on your website, Janet, or on your web browser?
No. I hope that was not what was on my screen.
So, so that to me is really the underpinning question that needs to be addressed. So, how do we formulate in a thermodynamically consistent manner open system dynamics? Clearly, and there are plenty of beautiful papers. I think some of the speakers have contributed already to the debate in quite an important manner. Someone in my group, so Gabriele De Chiara and Gabriel Landi have written a very, very, very interesting paper addressing part of this question, and I think it's a key one. No, the moment you go to strongly coupled systems, how do you account for description of open system dynamics in a way that is consistent with the laws of thermodynamics? That has implications in the way you define thermodynamic quantities, especially in this non-equilibrium regime that we are all interested in. And it has implications on, for instance, on transient features, which become particularly interesting the moment you cannot really rely on. Yeah, go ahead,
Mauro. I hate panel discussions because there's so much chatting and no pictures, and I love pictures. So can I show some pictures? Because I mean, you keep talking, I keep showing pictures. If that's okay.
Probably, see, an image is worth more than 100 words. So probably the pictures already.
I mean, this is some old talk slides, right? So I'm trying to supplement what you're saying with something that can people who don't know what you're talking about probably still don't know what you're talking about. So I think. So this is the question, right? The question is, when you have a system that's weakly coupled to the reservoir, that's when we write down the Gibbs state as the equilibrium state. And that's what you learn in undergraduate physics. You write down that where I have it here, you write down something that looks like this, the Gibbs state. And all of standard thermodynamics is built on this, everything you do in undergraduate physics. And what Mauro is correctly pointing out is this one big open discussion going on at the moment with many references that talks about the fact that when you have a system that interacts strongly with the reservoir, so the interaction part of the Hamiltonian here is non-zero, what do you do then? So you can ask that question dynamically, how is your system evolving in time? And you can ask that question statically. What would be, say, your reduced state of an entire equilibrium state? And that's sort of called the Hamiltonian of mean force program. And as Mauro said, there are many papers in this direction. So, but I agree with you. This is a big question, right? I mean, in 50 years' time, maybe students in physics classes learn a different thermodynamics than we were taught.
So as far as I'm concerned, I'm not particularly worried on whether or not we will come up with the formulation of a device or a machine. So I mean, what Nicole mentioned is incredibly relevant. I mean, so practical application they are important. But as far as I'm concerned, I would die happy if we could provide, say, a more consistent or a fully consistent, ideally, a more consistent description of open system dynamics in thermodynamic sense. If the development of this field achieves something close to that goal, then I would be absolutely happy with that.
I can add a little bit about fundamental questions, a different fundamental question. One is, what in quantum thermodynamics is actually non-classical? A lot of results have been derived that concern systems that are quantum, but maybe these behaviors can be mimicked by classical systems. So what makes something non-classical is itself a very difficult question. A high standard for non-classicality is contextuality. Suppose that you can imagine building a probabilistic sort of a model for an experiment. And suppose that there's something that looks rather irrelevant to the experiment. It's just part of the context. You know, am I wearing a red shirt or a yellow shirt? That we would expect wouldn't affect the experiment. But in quantum physics, a context that seems irrelevant can actually affect the statistics of measurement outcomes. So the example about a red shirt or a yellow shirt was actually not an example of a context that really we would expect to affect the outcome, the measurement statistics. But similarly, in quantum theory, if you are measuring some observable and it commutes with some other observable, you wouldn't expect that a measurement necessarily of that other observable would affect the measurement of your observable, but it can. So we say that quantum theory is contextual. In contrast, classical physics is non-contextual. So if you can prove that something is contextual, then it's non-classical and it can't be mimicked by classical systems. So it does tend to be difficult to prove that things are contextual, but it can be done. And there have been proofs that various information processing achievements and also various thermodynamic achievements are contextual and so non-classical. It's useful to figure out which of the results in the vast set of results that have been established within quantum thermodynamics can actually be within classical thermodynamics and which are especially non-classical. And also we expect that there are more effects that we might be able to observe, maybe performances of other types of engines or other types of refrigerators or other types of results of various interactions that could be truly non-classical, and it's useful to pinpoint those. So that's a very fundamental question within quantum thermodynamics that still merits work.
Maybe I can add my 2 cents since we're kind of talking about strong coupling and all that. I mean, I don't work on the topic really, but whenever I've read it, I always find interesting, and it's a tough problem. But just to comment on maybe something which I find interesting myself related to the topic is that if I take an arbitrary sort of many-body system that are routinely, created in the lab these days, whether it's a noisy intermediate scale quantum device that's functioning as some sort of computer, or whether it's a quantum simulator on an optical lattice, by default, I mean, the parts of this system are strongly coupled, and actually, you know, the dynamics there from an open systems perspective may not even be completely positive and trace preserving. You may not start from a product state. In fact, you typically don't, right? So, you know, often the sort of open systems techniques, the standard ones that we have, actually, they're not a very good descriptor of the dynamics. And I guess it is a bit not true to say that people for, you know, decades haven't really been thinking about those things. I mean, people have been studying, you know, non-equilibrium dynamics in those systems since Kubo and Alzheimer and all these people. One thing that I find quite amazing really is a very basic question there to me from an experimental perspective, which leads into it, is that, you know, in these techniques that people have used, which are typically perturbative or linear response or whatever, I mean, they've studied a lot, they've focused a lot on particle currents, electrical current, and this type of thing. But actually, if you ask any experimentalist in that field, how do you measure a heat current? And they'll tell you, we don't know. So it's not easy to measure a heat current. And I think that, you know, it would be very good if an experimentalist could measure a heat current, but actually they can't. I don't know. I mean, maybe people have some points of view on that, but it's not particularly easy. And that's the reason why you don't find a lot of studies of heat currents in the sort of literature for mesoscopics. Although you can compute those things theoretically, I mean, it's a problem.
Perhaps in the topic of experiments, before we move on, there is a question from the audience saying that what are the most important quantum thermodynamic experiments that all of you are looking forward to?
I can say something, but John may want first. No? Okay. Well, I would say the connection is between what Nicole was saying and what John was saying. So really this whole business of coherence, I think it has now also somewhat matured. I think there's a lot of results out there. You understand it much, much better than just a couple of years ago. And for example, Kenzo's talk just before the coffee break was a very nice illustration of different regimes where quantum coherence can sometimes be good, sometimes be bad. So we are in a much better situation now. But that has not been explored experimentally much at all. So there's like 1.5 experiments so far that have done a little bit in this direction. So that's clearly, from my point of view, something where I really am looking forward to experiments to understand better to what degree coherence really experimentally acts. Because what I believe is somehow I have the feeling that our maths might not fully describe what really happens in experiments. So as you know, when you work with an experimental group, it is never what you think as a theorist, what's going to happen in the experiment. Always you tell them something and they come back with something similar, but it's not the same. And so there's always a sort of cycle between interactions between theorists and experimentalists. And I think we theorists, most of us are probably theorists, can very much learn from such a cycle with experimental groups. And that's what I'm looking forward to.
Yeah, I mean, sorry if I can say that. Like, I think there, you know, everybody would admit, or anybody that's been around this bunch of, or this cohort of people or community for a while, like, people would admit that there is kind of an issue there, that, you know, that there probably isn't enough experiments, because, you know, not everybody is interested in thermodynamic properties of systems. But I think, like, there has been a good bit of progress, I mean, over the past couple of years. I mean, one of the things that's a joy about, you know, thinking thermodynamically, so to say, is that, you know, you sort of expect thermodynamics to apply to all systems. It's a difficult thing. I mean, you know, like, what are the experiments there for, I guess, is the question. I mean, so for example, you know, you could say that a quantum computing device, let's say a bunch of superconducting qubits or an ion trap that's made for simulation, you know, maybe you're interested in, you know, the heat dissipation there as a kind of pragmatic perspective as a thermodynamicist, or are you interested in proposing experimentalists to just verify your theory? It's always something that sort of confuses me a little as to what the role of the experiment. I mean, the real role of an experiment should be to discover stuff that we don't understand as theorists, and then the theorists go ahead and they try to understand it. But often I find, and this is not just a criticism of our field, but a criticism in general of even cold atoms, etc., is that often the experiments are set up to match the theory. And you know, I think it's good if we try to focus in and talk to experimentalists more, ask them what are the things you don't understand, and actually then try to construct the theories and models to understand.
They have millions and millions and millions of things they don't understand, and we don't. I mean, I'm again assuming that most of us are theorists. I think we tend to not do what they ask us because it's easier to do our fancy ideal world scenario, and that is part of the problem. I agree, John. I agree that it's not necessarily so sensible to make experiments basically produce what the theory predicts. Basically, if you make a theory for a harmonic oscillator and then you go in the lab and make sure you have a harmonic oscillator, you will get the dynamics and everything else, the physics of the harmonic oscillator. What else would you get? So that's of course true, but of course when you increase the complexity of any experiment, you push it outside the relevant region, and but you wouldn't even know that beforehand. So you wouldn't even know that you're not in that machine. So what we're actually looking for in experiments is when things don't go to plan. We do not look for things when they do go to plan. That's good. It's just like, okay, was expected. What we're actually looking for is when it doesn't go to plan. Much more interesting. Nicole?
I agree that I agree about a number of the points that have been mentioned. First of all, a lot of quantum thermodynamics has been theory. Second, experiments have been ramping up. We have great experimental platforms because people have been developing great control over quantum systems, largely because they're interested in building quantum computers, but we get to play with them too now. So this is a wonderful time to get into experiments for quantum thermodynamics. I agree with John that it's much more useful to propose an experiment that we really need. We don't know the answer already, we really need the experiment. Or to take an experiment that has some feature that's poorly understood and explain that feature. I agree with Janet that the experiments designed for theory proposals can have some benefits of their own. And so the question was originally, which are the experiments we're most excited about seeing? As a typical scientist, I'm excited most about what I'm doing right at the moment. So I have to say the experiment I'm excited about most at the moment is one of these experiments that was designed to check theory, but we were quite surprised that it seemed that our numerical simulations of an experiment appeared to work because we weren't sure that they would. So another opportunity that is in my list of opportunities that I prepared for this session is a growing subfield that started in quantum information theoretic thermodynamics. As mentioned by Janet, very often we in undergraduate statistical mechanics asks what happens if we have a small system interacting with a big bath weakly. We assume that the two exchange things, heat, particles, and the small system may thermalize under weak coupling to the canonical ensemble or the grand canonical ensemble or some other ensemble that depends on the things exchanged. We usually implicitly assume that the things exchanged are represented by Hermitian operators that commute with each other. This assumption of commutation is implicit. We almost never mention it. But a few years ago, a few of us realized there is this assumption that is behind some derivations of the form of the thermal state. And we're interested in quantum theory. Non-commutation is a hallmark of quantum theory. So what if the things exchanged by the system and the bath don't commute with each other? It turned out not to be even clear that the small system could thermalize. We're still not entirely certain that the small system will thermalize as well as it could if the things exchanged commuted with each other. So this propagated across quantum information theoretic thermodynamics in terms in abstract mathematical theoretical terms. So we learned a lot about this subject from that perspective. And just recently, over the past couple of years, my group and some other groups have been interested in making connections of the sort that John was talking about between quantum information theoretic thermodynamics and many body physics, the real physical world. We started asking, how would such a system look? What would be the things that could be exchanged? There are a lot of possibilities. But some collaborators and I proposed an experiment, a very simple one with a chain of qubits, and the things exchanged between system and bath would be the various components of the spin angular momentum. So an experiment happened to realize that protocol last week in a trapped ion lab. So hopefully we'll have a paper out soon. But so yes, that's what the experiments I'm most excited to see. But it has been useful. It is one of these experiments designed for theory, but it has been useful because the experimentalists have pushed us to figure out what is the best initial state to prepare. Why is that a useful initial state? Can we come up with a better one? What are the properties of initial state that we need? How do the types of couplings affect our predictions? And given that they actually could do more measurements than we anticipated, what other interesting questions would we like for them to answer? They can not only realize our goal, but they can do better. So what would be best for them to do? How can we best address the open questions of how a system gets to near whatever fixed point it's going to get near? So that's what I'm most excited about at the moment.
Maybe I can say very quickly. So again, I go back to my tantrum about quantum thermo and the actual inexistence of quantum thermo, and saying that it's a toolbox. So as far as I'm concerned, quantum thermodynamics is a toolbox to interpret the energy exchange processes occurring in an experiment. So I'm not sure. See, Chitrak, I'm not sure if I can point towards any important quantum thermodynamic experiments. They're all quantum thermodynamic experiments in a sense, and none of them is. They're all processes where some, say, parts of hopefully a composite system of a compound exchange energy among them. And in this regard, you can see most of the experiments taking place in the domain of quantum mechanics as quantum thermodynamics experiments. So I'm not sure that what to point towards, but if I would be really jumping off my chair, would be say something that would make me jump off my chair would be so I'm very old passion of mine is this optical control of mechanical systems. And so you have mechanical motions driven by light. And if you think about the typical setting of these experiments, the analogy with classical thermodynamics is very immediate. No? So you have a confined volume of space, you have a cavity, you have something that moves within, like a piston, you have a fluid inside, a medium inside, might be light, and you wonder, okay, can I use it to implement a machine, a device? And there have been proposals for the implementation of a machine based on these optomechanical settings. And then when you look at the performance of these devices, so when people go into the lab and try and make use of them, a bit because of the regime into which we have, say, these experiments take place. So I'm tapping from the points that have been raised by John, by Janet, and Nicole before me, a bit because of the platforms that we have are not yet fully ideal. Well, the performance of these devices is crap. I'm just using a technical argument or a technical terminology. They're awful. So I would be really interested in an experiment that demonstrates the consumption of a genuine quantum resource to enhance the performance of an optomechanical, say, piston in an engine, so an optomechanical engine. If that happens, I think that will be really not only interesting at the fundamental level, because it will give yet another line of yet another justification of why optomechanical experiments are indeed incredibly cool and incredibly interesting, in my opinion. And on the other hand, it will give the perspective of a possible, of a viable route to experimental advantages in a thermodynamic sense of quantum devices. yeah, so that would be really, really interesting as far as I'm concerned. Otherwise, I would be happy with any convincing interpretation of quantum experiments based on the toolbox of thermodynamics of quantum processes and systems. Having said that, there are fantastic experiments around, say, the experiment on the reversing the flux of heat.
Mauro, you're the most senior of us, and also a head of department, and it starts to show.
Say it again.
You're the most senior of us, and the most head of department. Yes.
Yeah.
So you're used to.
Right. He's not senior. He's old.
Yeah. We have a few more questions. Maybe we should move on to those because some of them are very interesting.
Yeah. So let's do that. So I'm gonna combine two of them. So they are within the field and outside of the field. So to cover the one within the field, both Varun and Soumitra are saying something along the lines that the field has grown so large that perhaps it's difficult to agree in definitions of work, and he also mentions the Landau's principle, etc. And then the question that Soumitra says is like, do you think this is going to hinder the progress of the field, or do you think that could be a convergence at some point? Perhaps I wouldn't go as far as
very quickly what I think. Because we've had this discussion before in one of the conferences, quantum thermodynamics conferences. So the issue of work, pet project of mine, I guess, and many of us. But it's been a big discussion over, I think, the last 10 years. Again, I have the feeling that we have come to some conclusions. But like Varun says, and I think Soumitra, it does look that we do not have just one single definition of work in the quantum regime. It's a little bit like entanglement in some very abstract way. Entanglement is also, you can define different ways of quantifying how much entanglement you have. And it does depend on the context in which you want to use it, which of those measures is sort of the right one. And I start to see it the same way for quantum work. Often it matters a little bit on the context. So if we ever actually want to build a quantum engine to really get work out, which I actually don't think, okay, just on the side, I don't think we're going to run a quantum power station. I do not think that. But if we did, we would probably want to connect it to the grid at some point. And the point is then how much do you enter into the power grid? That will be your efficiency to some degree, and how much coal do you burn or whatever you burn. That will be the efficiency. So, it depends on the particular application, what your good measure is. And I think we're okay with that from my point of view. I hand over to John, who's unmuted.
Well, I'm unmuted only by accident. I was quite happy to listen. No, I mean, I guess, I don't know, maybe taking back a bit of the question. Actually, I mean, with respect to this definition stuff, I mean, I don't know. I mean, I'm always a bit uneasy when I think about it. I mean, in particular, for work, I don't think there is an issue in the definition of work. I mean, because work is something that's always, in reference to the entire system in the bath, right? It's the energy change in the system in the bath. Defining things only at the system level is problematic. I think, if you want, that's definitely a problematic thing, because you've got coupling assumptions and all that kind of stuff. And remember as well that even in statistical mechanics, I mean, we don't have a unique entropy for systems not in the thermodynamic limit, right? So, I mean, I don't think really that worries me so much, as long as, what you're using makes an operational sense and you comply with the first and second laws of thermodynamics. I mean, then, I'm quite happy with that. I mean, I don't see such an issue. There's issues with definitions of heat in strong coupling, but I mean, the work thing, I don't really see a problem there. I mean, at least not for me anyway. I mean, I think it's crystal clear, but that's my take on that.
I agree with Janet. Physicists have a reputation for unifying things. especially because there's so much press surrounding notions of grand unified theories. Unification is great, but sometimes one size doesn't fit all, and sometimes unification is not the best strategy. And so sometimes the definition can depend on context, or the most useful way of thinking about a concept can depend on context and what your measurement capabilities are and what goal you're intending to achieve. So thermodynamicists or quantum thermodynamicists in this case might break this stereotype of the theoretical physicist.
I'm playing again the card of the old one, and I've seen so many, say, bubbles burst in this field that I would just be happy if it's not yet another one that bursts. So no, what I hope is that people won't lose interest. So whether or not there will be a convergence, I don't care, and I don't think it's actually the question that we should be worried about. What I hope is that people won't lose interest in developing an incredibly fundamental area and field. If that doesn't happen, then we will keep on having progresses. Otherwise, it will be yet another bubble burst in the general framework of quantum stuff.
Maybe this is a good point to actually join with the other question that in terms of progress for the theory of a fundamental level, that Mark is asking us that whether you think that quantum thermodynamics may perhaps play the same kind of synergies with other fields that we have seen. He puts as an example quantum information in high energy physics or condensed matter with AMO physics. Do you think that quantum thermodynamics could transcend its own field and touch in other areas of physics perhaps in the same way?
Definitely. And there are multiple people on this panel who work to connect quantum thermodynamics with other spheres of physics. So connections have been made to condensed matter, atomic, molecular, and optical physics, chemistry, high energy physics, and black hole physics. And there are lots of opportunities because there are lots of people out there who are interested in quantum physics, information, and energy. I agree that quantum thermodynamics involves a toolbox. So we can, and there are examples of this having happened, we can take our tools, head to another field and help people answer questions there, or we could discover new questions there, or we could gain insights from other fields and apply it to the more fundamental study of quantum thermodynamics. So I do think that, well, more precisely, the suggestion of connecting quantum thermodynamics as a field with other fields is another one of the opportunities on the list that I prepared for this panel. I agree that's an exciting path forward.
Sorry, can I just share this to sort of back up what Nicole just said? Can you see this slide?
Yes, we can.
Okay. Yeah, so that's from another, that's from another talk sometime, but this is just an example, right? So pretty much exactly what Nicole was just saying. There are many applications, and one of the things that at least stands behind the interest in quantum thermodynamics is really that we believe that it should be underpinning future technologies, because it has done so in the past. And the question really is which technologies on the nanoscales are going to need quantum thermodynamics. And of course, quantum computing seems a natural choice, but on the other hand, quantum computing is actually far away from thermodynamics because it's it's ground state. There's hardly any temperature. So maybe we should be looking at things that do have temperature, but that usually are classical. So we forget about this classical quantum distinction and maybe even make our hands dirty and look a little bit at classical systems that may soon become quantum. And one of those things is magnetism, for example. So when you look at hard drives where you're writing bits of information, so the way this is done is becoming smaller and smaller. So there's a lot of quantum stuff going on here. And this is an area where people want to use quantum tools, and they don't know the stuff that we know, and neither do we know the stuff that they know. And so we can actually, so here, for example, this is this LLG equation that the magnetism people use all the time. And what we did in this paper here is to derive it from quantum thermodynamics point of view or open quantum systems point of view. So basically, the point is one can help these people with our tools. And that's one example. And I think, Nicole, you had some other example in chemistry, right? Where you are looking at chemical reactions, for example. So that I think is also a really strong direction.
I had the opportunity to meet a chemist at the University of California, Berkeley, who was dealing with a small molecule, a molecular switch. It's very well known in chemistry. He plays with this in numerical simulations and so on all the time. It's just a rather complicated molecule because it's small, quantum, and far from equilibrium. And he thought it would be nice to derive a quite general bound on the probability that if a light is shown on this molecule so that it gains some energy, then it will switch configurations. And a general bound that doesn't depend on the specific details of the problem is in the purview of thermodynamics. So we used some tools from quantum information theoretic thermodynamics. We used a resource theory to model his molecule. And we were able to find such a bound. And then some other people in quantum thermodynamics took this up and found that if the environment is non-Markovian, then this can actually enhance the probability that the molecular switch will switch. So this was a wonderful opportunity to see that quantum thermodynamics can be useful to someone else too. Someone in chemistry, my collaborator is David Limmer. I hope that I think there are a lot of opportunities to do that if we can just find them. So have conversations with people outside of the field and see what questions, as Janet said, really need answering.
Yeah, maybe I can come in there. I mean, I agree with more or less everything that's been said. I mean, one of the things as well that I think that, you know, that the type of stuff that that people are developing in this sort of community, you know, for example, there's a lot of people coming maybe from traditional open systems background, etc. And you know, describing kind of currents and energy exchanges like Mauro mentioned earlier, is that you know, if you think about even mesoscopic physics, which is kind of a very mature area of condensed matter physics, where there's wonderful experiments being done, and you know, they've been studying fluctuations, etc., for decades now, you know, with tools that are very, very good. So, for instance, non-equilibrium Green's functions, all that type of stuff. Mostly, though, if you ask them, you know, they rely on sort of all of these techniques that they develop have, you know, various assumptions that allow them to work, whether that's a kind of weak coupling assumption or a perturbative assumption or a linear response assumption. So, you know, another scope that I see for the type of machinery or toolbox, as Mauro would call it, that's being developed is to try to figure out in their field, like, what are the difficult, where are the points at which their methodologies break, and if some of our methodologies within that realm of applicability can work. I think this is a very kind of sensible thing to do. It sounds a bit boring, but actually it's very important. I mean, to be able to see if you can find, it mightn't work in the entire parameter space. As Nicole said, it's not a completely unified way of description of energy exchanges. I mean, that would be too much to ask, but perhaps it works well in a certain realm of applicability within the experimental setup, and that's very valuable.
I don't have anything to add to what John just said. I think that will be a very valuable contribution to yet another area. In fact, say in my school there are people working on non-equilibrium Green function and ab initio modeling of say electron phonon interaction, and we are talking to them. They are interested in seeing the sort of approach that we as a community are developing to how that complements the sort of ab initio simulations and modeling that they are putting forward, that they have been developing since forever. So I completely agree with John.
Mm-hmm. Well, it looks that then there is a lot of opportunity to interact with other fields from quantum thermodynamics. Just so we know, we have 5 minutes left now of this panel, so it's perhaps a good time, unless another question comes out, for having some final remarks from each of you. So I don't know, for example, Nicole, would you like to start?
I appreciate the honor of being chosen to go first, but I will defer to someone else. So I have a moment to think, but thank you.
Of course, of course. Perhaps Janet, would you like to go first then?
Yeah, I'm not sure I have any fantastic closing remarks, to be honest. I think what we said is there are still many theoretical problems. Some of the advice from the panel was not to get too super technical all the time, because that can be misleading. So of course, doing some technical work is good sometimes, but pushing all the time in this direction is not so good. So linking it up with something concrete, maybe even an experiment, is a good direction. Linking it to different fields, chemistry, atomic physics, optomechanics, even technologies like magnetism and stuff, is a good idea, because you have to cross-check the assumptions you make. What is this, all the bits and pieces you write down, what does it correspond to? It's like, okay, I write X. What is X? You know, it does boil down to that at some point. And that has to happen in cycles. You know, you don't have to all the time worry about what exactly is X, but sometimes you do. Yeah, I think that's my closing comment. I hand over to the next volunteer.
Yeah, I think I echo Janet there, and I guess the message maybe that I've got from this panel discussion is, you know, it's great to find, you know, nice connections between, you know, quantum information theory and fundamental stuff, and I mean I find it nice. I've done work myself in that direction, but just maybe for younger people, I mean, just bear in mind that, you know, I mean, this is a bit controversial, but, you know, it's, if you think about, if you want to progress and make a career as a scientist, like, you know, it is very wise to try to root your work in physics. I mean, in the sense that, you know, will there be a quantum thermodynamics department in universities? Or, I mean, it's unlikely, it's too small of a field. But that doesn't, I mean, what you can have is, you know, you can have kind of, you know, whether it's in quantum information theory or condensed matter physics or statistical mechanics, to sort of ground yourself in a traditional area while taking some of the new stuff with you, at least is my advice to people. If, you know, but maybe it's a bit conservative, but at the same time, I feel, you know, it's a sensible thing to do, and it leads often to good insights, like, you know. Just try and ground yourself in physics, really, like as Janet was saying. I think it's a good idea.
Unless Nicole is ready for pitch. Okay, right. So again, just have fun. It's just have fun, and don't be afraid to tackle say seemingly crazy questions that might lead to negative outcomes. Say the non-expected outcome is always something to learn from. The other thing is probably not to contribute to the tendency that this community has to overhype a field. We don't know if what we are studying is really relevant for the performance of anything. We are exploring it and giving the message that, oh yeah, I mean, quantum effects are crucial for the working of nano engines, for the working principles of nano engines, might be misleading. So that's what we are studying. It's not what we have ascertained. Let's not overhype a field that is incredibly foundational, incredibly interesting, tantalizing, of potential at the technological level, but still in evolution. So have fun on one hand. Don't be say blown up too much on the other hand. Nicole.
Yeah, my remarks are similar to some of Mauro's. I agree with all of the practical advice that was given here, but this field is just so much fun. It's so exciting. I personally enjoyed it. I personally have enjoyed it so much. So if you choose to make part of your career here or your whole career here, or you're just stopping by because it sounds interesting and you want to learn something new, enjoy it. It really is an exciting place to be.
Thank you very much. Those were really nice remarks to finish, and I'm sure that the audience is pleased. So I think that with this, we can close the